Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 12 about an introduction to multivariate methods. And these methods are going to pertain to the next set of chapters: principal components analysis, cluster analysis, multivariate ANOVA, discriminant analysis, and classification. So having a firm grounding in what multivariate means and how linear combinations work, and a little bit about matrix multiplication and vector representations will make a really big impact on your success in the next several chapters. So in previous chapters, for example in analysis of covariance and COVA, we have used the word multiple regression. And the word multiple in that context refers to having several x variables in the regression model. And in all the models so far, we've only had a single number as a y variable. So the y has been a scalar, or a one-dimensional vector. So the multivariate word now refers to the response variable y. And that y, for each observation, may have several features in it. And in particular, say you wanted to understand something about a person, the response variable might include the person's age, their sex, their height and weight, their blood pressure, and that single response, which has 5 measurements in it, could be on the left-hand side of a regression model. So that is the sort of set of features that we're going to consider as a y variable from going forward. And we're going to limit ourselves to measurement data, basically continuous variables for the y-axis, for the y variables. There are methods for categorical data and for count data, but we're just going to focus on measurement data for now because that's a good scope for our class. And if you want to learn more about different other data types, there's lots of other statistics classes that our department offers. So let me introduce a couple examples that we'll see in later chapters and the types of methods that we'll use to take a look at these data sets. So the first example is turtle shells. So there's data on 3 dimensions of female painted turtles. So the shell of the turtle is basically explained by 3 dimensions: its height, its length, and its width. Basically the simplest characterization you could do, right? Because there's different shapes, perhaps a curvature of the shell, both on the top and on the bottom. But we're just focusing on these 3 dimensions. And the methods that we'll end up using are, one is you could use cluster analysis. Cluster analysis is a way for the computer to group observations that are similar in their multivariate features. So for example, if we had that, for the sake of these turtle shells, you might find that there are several sets of turtle shells that are similar in their height, length, and width, and those would be formed together as a cluster. For example, very large ones, and then small ones might cluster together. And the automated strategy of cluster analysis would help reveal structure in the observations that would be left then to the context expert, or you, to describe why you think those clusters came apart as they did. I've used that in my analysis of species of black cohosh, a medicinal plant that grows along the Appalachian Mountains, to identify how different plants may be related geographically. Another strategy is principal component analysis, which is a way to identify linear combinations of the measurements that account for most of the variation in the size and shape of the shells, of the turtle shells. For example, A turtle shell will increase in height, length, and width sort of all together as the turtle grows. It doesn't first get long and then get wide and then get high. They all sort of go together, which suggests that there's a way to combine these three variables into a single variable, maybe something like the mean or a sum or something else that helps us explain all three of these variables in a single variable. And principal component analysis is that strategy. Both of these are primarily descriptive techniques. They're not going to give us any way of testing specific hypotheses, but they're going to help us either visualize or understand high-dimensional data. Perhaps the most famous example used in multivariate methods is Ron Fisher's iris data, where for 3 species of iris, he collected 50 flowers, and for each one he measured the petal length and width as well as the sepal length and width. And if you have seen an iris, it basically has 3 flowers, and then it has what looks like 3 other, so it has 3 flower petals, and then for each flower, and then there's 3 other flower petals that are sort of between those main flowers, and that second level of petals are called the sepals. And so it turns out that these 3 species can separate very easily when you consider all 4 of these measurements all together. And so using that data, so suppose the sample means on each feature are computed within the 3 species. Are the means on all 4 traits significantly different across species? So meaning we've got a mean, so we would have a mean for sepal length for each species, we'll have a mean for sepal width, and so on for the petal length and petal width. We'll have 4 means. Well, if we consider all 4 means as a single point in a 4-dimensional space, then you can ask, is that 4-dimensional mean different between these 3 species? And that's where multivariate ANOVA allows us to test that hypothesis. We use just ANOVA to do a 1-dimensional response, and we use MANOVA to ask whether the multivariate mean differs between groups. Related to MANOVA is discriminant analysis. Discriminant analysis is a strategy for discriminating between groups by constructing a rule, which is based on a linear combination of the features that you've got, and that rule is the one that helps you best distinguish the species. So you can imagine that you've got like a piece of paper. Let's see, I'm going to wave my cursor around, and say you've got a bunch of points in the top left, which is one flower species, maybe another one down here in the middle, which is a second flower species, and then a third in the top right, which is a third flower species. So what discriminant analysis does is that you try to draw these lines, basically, that separate the classes, the 3 species. And so what are the best lines to partition the multivariate space in order to give you the best classification for new observations? So what's the best rule for distinguishing? I know this technique is used in so many applications. One that comes to mind is for credit card applications. So, as a college student, I know that you are probably bombarded by credit card companies and whether or not they're going to extend credit to you. And the types of offers that you get depend on your credit score, your sex, your age, how much you've been paying in taxes in the last years. Credit card companies have all sorts of information. I don't even know what they know. But they basically use that long list of features on you, right? So your age, your income, all those things, your credit score, and then classify you into some group. And that determines which advertisements you get. Yes, statistics is used for evil sometimes. All right, so all of these methods discussed here are inferential techniques, meaning that you can have a hypothesis in MANOVA, for example, and test that hypothesis. You can help perform classification in discriminant analysis, and I pull apart classification here as a separate thing because classification is a more general goal sometimes. So with that introduction, let's get down to the meat of multivariate statistics, which is linear combinations. So let's suppose we have data that are collected on P measurements or features. So this could be your age, your credit score, and so on. Okay, how much, what your income was for the last year. And most multivariate methods use linear combinations as the features for the basis of analysis. So here is y, just a new number, which is a linear combination of the x's. So these a's are real numbers. They can be 0, they could be 1, they could be -1, they can be the square root of 5, all those things. And y is a linear combination. Basically, we scale each x, and then we add all those values together. And here's 3 linear combinations just as an example, and 2 of these are ones that are really familiar to you. So this first linear combination has a 1 times 1x, sorry, 1 times x1, and then 0 for everything else. So that linear combination is simply x1. Okay, no big deal. What's the second one called? We have x1 up through xp. We're adding them together, dividing by p. That's called the mean. All right, what's the third one? You're maybe not familiar with this specific one. It's pretty arbitrary. 2 minus 4, 55, and so on. This one is just an example of a fairly arbitrary linear combination. All right. It will be helpful to use vector and matrix notation when we represent multivariate data. And so I'm going to show you a little bit about the geometry of vector and matrix operations in terms of linear combinations for when p equals 2, the number of predictors, because we can visualize that. So I made some plots here that give us some examples. Here's an example of a negative 45-degree rotation, and I'm going to scroll down to the plot first, and then we'll come back. On the left-hand side, our axes are x1 and x2. And we have a point here in space. This point is 1 over the square root of 2 and 1 over the square root of 2. So 1 over the square root of 2 is about 0.7. So it's 0.7 and 0.7. And there's a point. So the negative 45-degree rotation, so 45 degrees is, we start at the right axis, the x-axis, and we move counterclockwise. That's a positive rotation. And so a negative 45-degree rotation will take this point and rotate it down to the axis, 45 degrees. So basically think of this point as connected to an arm attached at the origin, and then rotate at the origin to come down. Okay, so we've got this ellipse here and the point, and so that rotation, if we rotate it down, looks like what we have on the axis on the right. But now this is in terms of y1 and y2. What we'd like to write down is what is the linear combinations of x1 and x2 that convert from the x-axis to the y-axis to give us that new orientation of our data. Let me scroll up. So this is that linear combination. If we add the x's together and divide by the square root of 2, and if we take the difference of the x's and divide by the square root of 2, that relationship gives us that rotation. And that will work for every point in the plane. It will all, so that's why this ellipse, this whole ellipse rotated to now be horizontal. And if you solve for any point, for example, if you solve for 1 over the square root of 2, in this case, let's see how this works out. Can we do this in our heads? 1 over the square root of 2 plus 1 over the square root of 2, that's 2 over the square root of 2, divided by the square root of 2, so the two square roots of 2 in the denominator multiply, and you get 2 in the denominator, and we had 2 in the numerator, so 2 divided by 2 is 1. So we have 1 for y1. Let me page down. So 1 for y1, that worked. Then if we have 1 over the square root of 2 minus 1 over the square root of 2, that's 0. y2 equals 0. Okay, we have confirmed that it works for that blue point. And you can trust me that it works for every other point as well. Or not, you don't have to trust me. You can work it out for yourself for every other point in the plane. All right, let's look at where some of this can become super useful. So let's look at a plot now of two groups. I've got two ellipses here in the x1, x2 space. Group 1 is the one on the upper left. Group 2 is lower right. And imagine a rotation that is a linear combination that gets us from the x-axis to the y-axis that brings us here to the right. You know, maybe one more feature I want to describe that what I'm doing here. What are these green lines? Y1, this green line here is the y1 axis, which ends up being the horizontal axis down here. So the green line goes through the blue point, right through the long axis of the ellipse, and that over here goes horizontally through the blue point through the long way of the ellipse. Y2 is this axis, which goes the short way through the ellipse. Same thing here, y2 is on the vertical axis. So I'm basically on the left plot putting both axes down. The x's go horizontally and vertically, and the y-axes have some different orientation. And then on the right, I'm showing the y-axes all by themselves. So now you can see this a little clearer. So y1 is this horizontal line. Notice y1 separates these two groups perfectly, and y2 goes through the center of both of them. So now here's y1 as the thick bar going horizontally, and y2 is vertical. So you can imagine a situation where you want to ask the question, is the mean for groups 1 and 2 different from each other? And you might phrase it a little better than that. Are the means different from each other instead of is? And you can see in the x1 direction, there's a lot of overlap between groups 1 and 2. So you may test that and not find a difference. Similarly for x2, you could test this direction. There's quite a bit of overlap this way too, and possibly not see a difference in means. However, if you look at both variables at the same time and discover this linear combination y1 and y2, so y1 now does not perfectly does not discriminate, because horizontally these groups overlap perfectly, but along the axis of y2 these two groups separate perfectly. So with respect to y2, we found a rule that separates these two groups, and that would end up being the rule in discriminant analysis. Okay, so that's sort of what this paragraph says. For an arbitrary rotation, which is what we did up here, so in this plot I've got theta here. Theta is a Greek letter TH. It's not just t because that's tau. So it's a Greek letter th. And it's intended to be this angle. So if I want to rotate the data from where the y1 axis is sloped downward, if you go clockwise, that's a negative angle rotation, flat. And so that is what this paragraph is saying. I'm going to rotate by negative theta degrees. Here's the general rule for that rotation, which some of you may have seen in a linear algebra class. Cosine theta times x1, sine theta times x2, and then you flip the cosine and sine and you put a negative on the sine, and that will for the second variable. And we can check to see whether this gives us what we thought it did. Earlier we saw that cosine of negative 45 degrees was 0.7, which was what we saw as 1 over the square root of 2, and those give the same numbers. Similarly, we should see that for, that's sine of the positive. Okay. So those numbers work out the way we expect them to. That is, if I page up, that's where all these square roots of 2 come from. Page back down. Okay, great. Let's talk about vector and matrix notation. We're almost finished with this video. So a vector is a string of numbers or variables that are stored either in a row or column. By default, the word vector refers to a column vector, which is located here. So I've created a vector x, which includes elements x1, x2, down to xp. And you can identify a specific row of x by a certain subscript. So this has become fairly similar, or familiar to you by when you're programming in R and you're selecting elements out of a data frame. So you can imagine this is just a row or a column in a data frame. We can transpose a vector, which I'll use this notation, a prime, in the superscript, to change a column vector, which is vertical here, to a row vector, which is horizontal. So x prime converts it from being a column to a row. And we'll use that sparingly in this class, I promise. All right, let's suppose we have data on p features. So we've got x1 up to xp for a sample of n individuals. So maybe each person in the class. Then the data for a person in class will be identified as xi, and the features for that individual will be xi1, xi2, down to xip, each of those features for that person. And if you put all the xi's together into a table, we'll get a matrix. Here we've got a row for each individual. So this is observation 1, this is observation 2, and we've got that string of features for each individual. This is going to be familiar to you as well. This is basically how we store data in a data frame. From this matrix, we can calculate the mean by, over each column, calculating the mean. So what is the mean for over individuals for feature 1? That's x1 bar, and so on for each feature. So we can have the grand mean x bar, which is the mean of each feature over the individuals that were measured. Similarly, we can, or to extend that, we can also calculate a sample variance-covariance matrix. Now, we've talked a lot in class about variances, but we have not, and we have created covariance matrices, though we often look at correlation matrices because they are scale-free. And so this is how you can calculate those variance-covariance matrices. Here is the variance-covariance matrix S. SII is the variance for feature I. So SII here, if the II was 1, we'd have each observation minus the mean, square that, add them all up, divide by n minus 1. And if you took the square root of that, you'd have the standard deviation. So this is the variance for each feature, and those are the values that are on the diagonal of the variance-covariance matrix. So the diagonal is the variances, and all the values on the off-diagonals are covariances. And those are symmetric, so that S12 is the same as S21. And so this formula here, Sij, gives you the covariances. We have for feature I in this case, the difference between any observation and its mean, and then for feature J we have that observation and its mean, and then we multiply those together, add them up, divide by n minus 1. And notice that if I and j were equal to each other, it reduces to the equation above. Alright, so that's what all that says. And this formula is simplified by using matrix notation. So if this is the vector for, let's see, k goes from 1 to n. There's n individuals. So for each individual, we've got the vector of the p-dimensional vector of all the values that are taken. And we subtract the mean from that and do that again, but take the matrix transpose. So this left-hand equation is a column, or what's in this left parentheses, that's a column, and this is a row. And when you multiply a column and a row, you end up getting a square matrix. So this column has p is of length p, so it has p rows in one column. This is just the opposite. It has it has p columns in one row. And when you put that together, if I scroll up a little bit, you'll get something that is p by p. And so for each individual, you perform this operation, add all those square matrices together, divide by n minus 1, and you get the matrix above, the variance-covariance matrix. And then you don't have to call it the variance-covariance matrix. You can just call it the covariance matrix. Similarly, this is what we more frequently calculate, is the correlation matrix. And it's simply starting with all the elements in the covariance matrix. So Sij is the covariance, but then dividing it by Sii and Sjj. Those are the variance terms that are associated with that covariance term, and take the square root. So if I scroll up to here, for example, S12, if you wanted the correlation between feature 1 and 2, you would take the covariance, divide it by this variance and this variance, those numbers on the diagonal, and then take the square root of that denominator. Scroll back down. So that's what this is. All right. So that would be Rij. And one feature you can see is that Rii, if I and j are equal to each other, will give 1 on those diagonals, because this is Sii, This is SII and this is SII. You multiply these together and take the square root, you get SII. So the ratio is 1. Finally, in many applications, the data are going to be standardized, and the word standardized often means that we're going to do a location scale transformation to give each variable mean 0 and variance equals 1 for each feature. And this is called a z-score transformation. It's called a z-score transformation because if the data happen to follow a normal distribution, any standard normal distribution or any normal distribution with a particular mean and a variance, if you perform this transformation where you, for each observation, you subtract the mean and divide by the standard deviation, you will then get a normal distribution with mean 0 and variance 1. And z is the variable we use for the standard normal distribution. So that's called a z-score transformation. All right, let's look at an example. Suppose we've got 3 features, x1, x2, and x3, to be reaction times on 3 visual stimuli named A, B, and C, respectively. Suppose you're given the following summaries based on a sample of 30 individuals. So you can imagine that you are one of these individuals, you sit down, you've got a button in your hand, and you're presented with 3 visual stimuli, and you have to press the button in response to seeing that stimulus. So for the first stimulus, over the 30 subjects, the mean is 4 seconds. That seems really long. Maybe these are not seconds. These certainly aren't milliseconds, so I'm not sure what the scale is. Visual stimulus, it could be something like, say you start with something that's all black, and then the contrast increases until you can actually make out what something is, and that could take some length of time. Okay, so who knows what these are? This is just a stupid example anyway. So anyway, we've got the mean as being 4, 5, and 4.7. Here are the variance covariances. So the variances are basically roughly 2.5 on the diagonal and a little bit less than 2 on the off diagonals. It seems that x1 and x2, they have a larger covariance, so they're probably more related than, say, 1 and 3, which have a lower covariance. Covariances can be positive or negative, and the signs of the covariances will be the same as the signs for the correlations between the features. So here we actually do have fairly high correlation between features 1 and 2, and similar correlations between features 1 and 3, that's this one, and 2 and 3, that's 0.7. All right. All that was just reading off there. All right. Matrix notation to summarize linear combinations. So this is just going to be how you do multiplication between vectors. Suppose we've got a feature vector. So here x is a column vector and x prime then is a row vector. So here's the row, x1 to xp. And we want to take a linear combination of these x's by putting these coefficients in front of them, a1, a2, up to ap. In using matrix algebra, x1 is the matrix product of 2 vectors. A, so you can think of A as being a column vector, something that's vertical. A prime then is going to be a row vector, horizontal. And that row vector, horizontal, multiplied by x, which is a column vector, will give us this exact expression. The first element of A and the first element of x will multiply together, and then that will add with the product of the second elements, and so on. And this is in linear algebra, this is called the dot product between 2 vectors. there are some results here about what happens when you've got use a linear combination of the mean of x. So say x starts off having the mean x bar, and you want to know what is the mean of y bar after you take this linear combination a prime times x. So for the mean, it's really simple. You just, for each feature, you multiply by the coefficient with the mean, and that gives you a prime times x bar is the new mean for y bar. This is where it gets interesting, is for the variances. So we have S, which was the covariance matrix for x. So what happens when you multiply x times a prime? So what is the variance for y is the question. Well, if you take that A matrix and pre-multiply by A transpose and post-multiply by A, that will convert all of the individual covariance terms appropriately, scaling them by the A, all the A terms, to give us a new variance term, covariance matrix for y. Similarly, if you've got, here's just another arbitrary, actually, I don't think we really need to know that part. Okay, just another result. As a final example, let's use the data from the stimulus example from previously and look at this linear combination, 1, 1, 1 times x1, x2, x3. This linear combination is called the sum. So we'll look at the total reaction time per individual over these three tasks. The mean reaction time for y bar, and there's a typo here. You should ignore this line and let this be y bar. So y bar equals this quantity, and I'm just substituting x bar in for this mean. And so we're just going to add those three mean values and get 13.7. Finally, the variance with this linear combination. The variance for this linear combination, we pre-multiply by the A prime matrix, so 1, 1, 1. We post-multiply by the column vector of A times the matrix S. So what I should have done here is pasted in, if I page up for a moment, this S matrix, which is this 3 by 3 matrix. So for each element of our new covariance matrix Y, which is actually only going to be one-dimensional big, this ends up simplifying to be a summation of all the variance covariance values in that matrix. So if you take all of these numbers and add them together, and just sort of by eye, it looks like we got like 5, 6, 6 times 3, roughly about 18, and scroll back down, we add all those together, we get about 18.5 is the variance now for the sum of all the reaction times. And that is a very brief introduction to linear combinations and multivariate methods.